free fall. And first, let's go back to how we started the year. And we started the year with the big three. There's our position equation, velocity equation, and the v squared equation or no time equation. We traditionally introduce those in a horizontal perspective. So we're talking about a truck, a car, a runner, a train, things that are moving simply left or right. And so we usually use x's, and then all these other unknown quantities all depend on the situation. We've discussed in class that x naught can be positive or negative depending on whether you're left or right. V naught can be negative and positive depending on whether you're initially moving left or right. This could be a minus sign if the acceleration is negative, and so on. This plus sign can be a minus if you're slowing down, and it's a positive sign if you're speeding up. So what we do is we take these three equations and we adapt them to vertical. There are lots of vertical situations. Now, we can talk about rocket ships and parachutes and other things that have different accelerations other than just g. But if we're talking about free fall, we are talking about an object under the influence of gravity and gravity only. So if we're in, quote, free fall, an object is dropped or thrown and it's just under the influence of gravity, we know what happens. It accelerates at exactly 9.8 meters per second squared. Okay, so we take these big three horizontal equations and we adjust them to more of a vertical sense. So instead of a random plus 1/2 at squared, now we have a minus 1/2 gt squared. Instead of just v naught plus at, now we know what happens. So it's just going to be v naught minus gt. This sign actually can be positive or negative because if an object was already moving down and then gravity is going to speed it up, that actually does have to be a plus. But again, the acceleration is going to be g, and instead of delta x, it's some like delta h. Okay, so let's go through these questions. We just drop a ball from 50 meters. How long does it take to hit the ground? I'm going to always suggest that we start by writing the abstract equation first, meaning start with just letters. Write the equation you think happens, and then we can identify what is all going on. So we dropped it, so v naught's equal to 0. We want it to hit the ground, so we want y is equal to 0. And all I do is substitute those values into the highlighted equation, and I get this equation, and then I just solve, and I get 3.19 seconds. Okay, now let's keep going. How fast will it be moving just before it hits the ground? Clearly, once it hits the ground, it's going to change its velocity. So when we say how fast is it moving before it hits the ground, we're talking about the moment before it hits the ground. So if you're interested in how fast, I understand that's a speed, but we're still going to use the velocity equation to figure it out. So we're going to use that guy. And we know we were dropped, and that's a 0 initial velocity. We know it's going to accelerate down at 9.8, and we're going to be in the air for 3.19 seconds. Since we already know how long the object is in the air for, well, then we know how long gravity is going to act. So we just take 9.8 and multiply by that, and we get negative 31.26, which is the velocity, negative because it's down. Since the question asked how fast, it's really asking for the speed, which is the absolute value, right? The magnitude. And so really, if you're answering this question, you should give me a positive 31.26. All right, how high is the ball after 2 seconds? Well, it's fallen a certain distance, but we can just use the position equation. We want to know how high it is when time is 2. That's dropped, so v naught is still 0. The initial height is 50, and so I'm just plugging into this equation and solving. And from like a more of a math point of view, I'm really saying y of 2. What is the height when time is 2? And you get 30.4 meters. And again, of course, that is above the ground. All right, let's go on to this next one. This one, I'm going to give you different information to start. I say a ball is thrown up, and I know it takes 5 seconds to reach max height. This is one of the key pieces. Think about it. At max height, the vertical velocity is 0, so it stopped. So if we use the velocity equation, we know that the final velocity is 0. We don't know what we threw it at, but we know it's under the influence of gravity. Gravity is going to slow us down in this case by 9.8 meters per second for every second, 4 or 5 seconds. So we just take 9.8 times 5 and we get 49. We must have been thrown up at 49 meters per second if it took gravity 5 seconds to stop us. Okay, how high did it go? Well, that's an interesting question. Let's go ahead and use the v squared equation in this case, because I'm interested in the distance. Now, I wouldn't have had to. I could have used other things now that I know initial velocity. I could have wrote a position equation and just plugged in 5 and got it, but I thought let's use the v squared equation. This is going to relate how fast we were thrown at the beginning, 49, under the influence of gravity, stopping at the top, and all we had to do was figure out h. What's that distance that it took us to slow down, and you get 122.5. Okay, total flight time. Number one, we really have to start believing in symmetry. Okay, so what happens is gravity slows you down, but then it speeds you up. And since it takes 5 seconds to go up and 5 seconds to go down, you can imagine that these two questions are very much related. What was the total flight time? Well, it was double. So it took 5 up and 5 down. Well, if it took 5 seconds to go up and 5 seconds to go down, then you actually came back at exactly 49 meters per second as well. Think about symmetry. You can prove it if you really wanted to just figure out when h was equal to 0 and you solve this equation, you'll get 10 seconds, meaning it took 10 seconds to go up and down. Gravity is going to slow it down by 9.8 meters per second for every second on the way up, 5 seconds. And then it's going to speed it up by 9.8 meters per second for every second, 5 seconds on the way down. So of course it has to get to the exact same speed. Now, if we included air resistance, which we typically call drag, then all bets are off and it's different. There's no longer any symmetry, okay? But as long as we're just in free fall, if you throw it up, it's going to come right back down that exact same speed and the exact same amount of time. If you graphed it, it would be a nice symmetrical parabola. Think about graphing this, and it would even make more sense how that symmetry plays a role. All right, now let's climb up to a building. Instead of dropping something, let's throw it down. We could have thrown it up. I just thought maybe it was more fun to throw this thing down. So again, I'm going to start the problem by writing in the abstract letters. Then I'm going to plug in stuff. So I want it to hit the ground, 0. I threw it from a building of 70. I threw it down, so I used a minus sign there. And I know gravity accelerates it down, so that's a minus sign. And in this case, this is a quadratic. I'm just going to use the graph to solve. So I think I actually put it in to Desmos, but you guys can use your graphing calculator. You could use the quadratic formula if you want, but that's the time I got at which the height of it was 0. All right, what's its final velocity? And again, when I say final velocity, I mean the velocity just before it hits the ground. And then all I'm doing is using the v squared equation. I'm interested in velocity, throw out the velocity equation. So v equals negative 10 to start minus 9.8 for that amount of time. And you get that negative 38 value. If I drop a ball from a building, how far has it fallen in 1 second? Again, don't say 9.8 meters. Like, wait a second. It was accelerating at 9.8 meters per second squared. Didn't it fall 9.8 meters in 1 second? No, that's not true. It got to a speed of 9.8 meters per second at the end of that second. It wasn't going 9.8 meters per second the entire time. It started out at 0. It worked its way up to 9.8 meters per second. So no, it did not fall 9.8 meters. Now it is traveling at a speed of 9.8 meters per second at the end of 1 second, but it actually only goes 4.9, which really, if you think about, you can use this equation to figure out how far it would fall in 1 second. But you can also think, well, if it started at 0 and it uniformly accelerated to 9.8, then isn't the average have to be 4.9? And if it averaged 4.9 meters per second for that first second, didn't have to fall 4.9 meters? Think that through, but you actually could have gotten that easier without even using these equations. All right, 7, 8, and 9 are really like the big boy questions. The other ones are kind of just warm-ups, get you going, thinking about free fall. So 7, there are two objects, A and B. A is dropped, B is dropped 2 seconds later. Once both objects are in the air, meaning they're in free fall, the question is, do they start to separate or do they maintain that same distance? And so if you think about, after 2 seconds, rock A is now moving 19.6 meters per second down. Right? It's got 2 seconds to speed up by 9.8 meters per second. This is the work, but you probably could have done it in your head. And then if you think about, A will always be moving faster than B, thus it will continue to get further and further and further and further away from B. Just think, after 3 seconds of A being in the air, isn't it now going, what, 29.4 meters per second, and B is only going 9.8 meters per second. See how it's even going faster? It's always moving faster. So for every second it's in the air, it's just going to move a bigger distance in that second. Both rocks, however, will both continue to increase their speed by 9.8 meters per second, but it's not like rock B can ever catch rock A. Rock A will always be moving faster, thus will separate. All right, that was a little more conceptual, but you can prove it. You can just go through numbers if you wanted to. All right, number 8. Rock C is dropped and rock D is thrown upwards. They smash together exactly halfway up the building. Let's figure out how fast rock D must have been thrown up from the ground. So the first thing we want to do is let's figure out when rock C is actually halfway. Because again, it does say they're going to meet halfway. So what I did is I put in a final height of 50, initial height of 100, and then I dropped rock C with an initial velocity of 0 and figured out that took it 3.19 seconds. Okay, so now I know that rock D is also in the air for 3.19 seconds. And so then I figured out, well, how fast do I have to throw rock D in order to be in the air for 3.19 seconds and reach a height of 50? Remember, I need them to smash. I need them to both be at 50. And that's what this is saying. Go to 50, start from the ground. How fast do I throw you if I know you're in the air for 3.19 seconds and I know you're under the influence of gravity? And it turns out that if you throw that thing at 31.3 meters per second, bang, the two rocks will smash. All right, last but not least, this is probably my favorite one. I always love collision questions. Rock E is thrown down at 10 meters per second from a height of 30. Rock F is thrown up at 15 meters per second from the ground. And the question is, where do they collide and how long does it take? And the beauty of this one is I actually answer this question first. How long? One of the key pieces is this, and it seems obvious once you read it. You want these two rocks to collide. What does that even mean? Well, we want their heights to be equal. So here's the standard position equation. This is the height of rock E. This is me filling in for F. E starts up, thrown down, gravity. Rock F starts on the ground, thrown up at 15, gravity. And so what I want E equal to F. I want them to be at the same heights. So set them equal to each other. And actually it's kind of cool because if you set them equal to each other, they both have this same term on both sides of the equation, and you can just cross that out. And then you're left with adding 10 to the side and dividing by 25, and you can show that it actually took 1.2 seconds for them to collide. And then if you want to know where they're located, you can take the 1.2 and plug it in here for time and here for time, and then you can actually prove to yourself that they actually collided exactly at 10.944 meters, which is pretty cool. Okay, hopefully this video helped you with these questions, and if not, we can talk more in class tomorrow.